Okay, so good afternoon, everyone. We've heard quite a bit today about the XY gate, this new gate that Rigetti has native to its devices. And we've also heard some stuff about its application to QAOA. And in this talk, that's something that I want to explore a bit more, particularly with the reduction of gate depth. Also kind of connecting to the message of the last presentation. This is more about the push from the NISQ application, the NISQ algorithms rather than the business use cases. So just to introduce a little bit about Entropica Labs, my company. We're based in Singapore, a spin-off of the Center for Quantum Technologies at the National University of Singapore. What we do is kind of develop tools and software and explore applications for quantum machine learning and optimization. But we take a very hardware-driven approach, so that's kind of the message of exploring the best features that you have on the hardware today, really getting used to and implementing these algorithms even on small devices, noisy devices, and really learning how to improve these and scale them as the hardware becomes better. So just to note, we have a package that we released for the Forest platform. So this is for QAOA. It integrates natively with the QVM and QPU, Rigetti's system. It has a ton of features for basically simplifying the workflows of QAOA and deploying on the different on the QVM and QPU. So if you're interested in QAOA and applications, I'd encourage you to take a look at the website, our documentation, and our GitHub page. We're always happy to receive feedback on it. So the goal is basically to show how the native XY gate can improve particular QAOA computation. So I'll just introduce the problem, show the implementation details, and then the results. So this is the problem I'm interested in. It's a really, really simple QAOA problem. It's just a triangular graph. This is the cost Hamiltonian. Basically, what happens here is what you're trying to do is minimize this Hamiltonian. Each of these terms really wants the qubits involved to be in opposite states, right? So for this term here, qubit 1 should be in state 0 and qubit 2 should be in state 1 or vice versa. And you want to minimize all of these terms. But because of this triangularity, it's not possible to minimize all of those terms simultaneously. And this is what we call frustration in physics, right? It's a phenomenon that really occurs in hard optimization problems. So one point to make is that that's the kind of problem, even though this is a really trivial version of it, that you should really start to seek advantage if you believe that QAOA would actually deliver that. So I have this edge here, this edge that has an omega attached to it. These other two have a constant weight on them. And I'm going to be interested in varying this omega and seeing what the probability distribution looks like. And ultimately, I want to know, is the QPU actually really giving out a good probability distribution as I change this such that I could distinguish two different graph instances with slightly different couplings. So if you take the case where omega is just smaller than 1, so this is the probability distribution you get if you run just a simple depth 1 QAOA. This is just from the simulator using the optimal parameters for depth 1. What you see is that basically the solution, and probably the experts will see why immediately, these two qubits on this weighted edge should be in the same state, 0, 0, both of them in 0, or both of them in 1. If I go to the opposite extreme, where omega is larger than 1, then we get the opposite case. So now these two qubits should be in opposite states. So one of them should be in 1, and the other should be in 0. And the case that sits right in the middle is just where omega is equal to 1, where everything is kind of degenerate except for the 0, 0, 0, or 1, 1, 1, which are heavily suppressed because you can't have, in this configuration, all three qubits in the same state without a very high energy penalty. So what I'm interested in is really looking at the ratio of, so you see as we sweep through 1, the value 1 on this edge, the probability distribution changes and the ground states or the optimal states change from being a situation where these two qubits are in the same state to where they actually are in opposite states. And I'm just going to define a metric, which is the the sum of all the probabilities where these qubits are in opposite states to the sum of the probabilities where they're in the same state. So basically taking the heights of these bars as the metric for the performance here. So again, this is just on the simulator for now. If you vary this parameter omega, at each omega you just feed in the optimal p equals 1 QAOA angles and you plot this ratio. It looks fairly nice. It's a fairly well-behaved function, and you see that it kind of it reaches, the two are the same as we saw in the previous slide where the ratio equals 1 when this omega on that weighted edge is equal to 1. So the question is, do we see something like this on the QPU? And what happens when we have noise in the statistics and so on? So I'm going to embed this sensitive edge in a pair of qubits that are not natively connected on the device. So this is actually an interesting question, even if those two are connected on the native device, what does the result look like? But for the purposes of showing the XY gate, I want to embed this in a pair of qubits that are not natively connected. And if you think about larger instances, more interesting instances where you might have many edges, where you have some kind of sensitivity to the value on a particular edge, it might not always be easy for you to put your sensitive edges on pairs of qubits that are natively coupled, right? So this could become a problem as you start to scale up, and you would have to perform swaps. So I'm going to use the ASPIM4 A, just a 3-qubit device, and the mapping is this. So this is going to be qubit 1, qubit 2, qubit 3, and I'm going to have to couple these two qubits with this swap gate. So this is the kind of characteristic schematic picture of the circuit. So this gate here is coupling these two qubits. This gate here is then coupling these two. But to couple these two, I need to do a swap. That's what this kind of X thing is here. And then I do some other rotations and I measure and get the probability distributions. Now I can perform this swap in one of two ways. I can use the CZ, which is kind of the old way where you would use 3 CZs or 3 C naughts to implement the swap. Or I can do it as we saw earlier with one XY gate and one CZ gate, so thereby reducing the 2-qubit gate depth by 1. And so here are the results. So the green curve is just the simulator, the perfect result. The blue is using this kind of X, Y, and CZ swap, and the orange is using the 3 CZs. Okay. Now, each point here on these two cases is the mean. So I've taken many samples of this ratio for different values at each value of omega and plotted it, and also the standard deviation, which in the orange, in the CZ swap case, is this big orange bar. And I don't know if you can see these kind of blue arrows for the XY CZ swap. So basically what you can see is that the XY swap gets a little bit closer to the real answer than the CZ, although they both kind of largely have the same slope. But I think the interesting thing here about the XY is that the standard deviation is much smaller compared to the CZ swap. It's actually an order of magnitude smaller if you dig into the numbers here, at least for this case. So that to me gives me two interesting things. It means that firstly, to estimate the mean within some accuracy, I need to take significantly fewer samples from the processor. So, you know, if I'm worried about the cost of quantum computing or something like that, that could be a really good feature for me to have. And secondly, if you look at simply if you just look at the scale of the standard deviation compared to the variation of this function in the whole range here for the CZ, it's going to be very hard to distinguish two kind of neighboring problem instances, perhaps if you only have a kind of finite number of measurements or fixed number of measurements. So for example, 0.9 and 1.1 for this constant here, if you have a fixed number of measurements, it might be difficult to actually distinguish those two cases, and therefore you might not see the correct output probability distribution. So I think the XY gate is a very kind of promising thing for QAOA. I've shown it in this problem instance, which I think is interesting because it has this frustration effect where you get changes in the ground state solutions as you change this parameter. So I think there's interesting future work to do here. So thanks for your attention.